Hi, we at Group Golf. We've designed and developed a simulation of a differential analyzer, abbreviated as DA, running as a single-page application. It is publicly accessible, and the code is open source to encourage further development. The links for the program and source code are found on screen. The program comes with several example configurations, or you can build your own from scratch. Here's Sophie to explain what a differential analyzer is.
The differential analyzer was a type of mechanical analog computer designed to solve nonlinear differential equations by numerical integration. Vannevar Bush constructed the first general-purpose differential analyzer in 1928, with the Meccano version later built here at the University of Cambridge by Maurice Wilkes in 1938. They saw widespread use before electronic computers and were notably used during World War II in calculating ballistic firing tables. Simon will further explain how did a differential analyzer work.
The differential analyzer consists of simple mechanical devices, shafts, one of which is powered by a motor, cross-connect, gear pair ratios, and summers, with the latter acting like the differential in a car to add or subtract two input shafts. Function tables and multipliers required human operators, whereas in ours, they are automated. We also have integrators which integrate a shaft with respect to another shaft, usually representing time. Output tables plot the input and output of any two shafts onto the canvas. Aaron will show how this works in our simulation.
Here we have a partially completed differential analyzer with shafts already for t and x. To finish it, we need to add a function table, an output table, and an integrator. We also need to add a shaft for the integral of x, which we can resize, and another shaft for the second input to the output table. We can also add some cross-connects to these shafts. We change the function table to be x with the y range between 0 and 10, and the output table between 0 and 50. We can see blue is x and red is its integral. We can also change the function table to be x squared between 0 and 100, and the output table between 0 and 340. We can again see blue is x squared and red is its integral. I will pass you to Hanzhang for a more complicated example.
We invited Professor Hunt from Cambridge Engineering to pose us a challenge. He suggested we try to model the motion of a double pendulum. This is our completed solution. Fortunately, our simulator allows for constructions of larger configurations than on the original physical machines. The two output tables here show the movements of the lower and upper pendulums. We show that the movements of our predictions closely match those on the physical apparatus in the mechanical laboratory, where the lower pendulum stays below horizontal. For larger deflections, our prediction correctly shows that the system is chaotic. But what challenges do we face creating the simulator?
Our main challenges lie in communication between front-end UI and back-end core, a problem we solved by passing configuration of one subsystem into a JSON file for the other to read. Some minor challenges lie in deciding between trade-offs. So, for example, we moved away from a realistic-looking UI to adopt a minimalistic one to provide simplicity. By integrating the UI and the core, the configuration of our machine represents a declarative domain-specific programming language, one that, while we have not yet proven, we believe is Turing complete, a goal we will later try and prove. We believe that our simulation can successfully be used in education purposes, showing how a differential analyzer would have worked, as very few are still in operational order today. Thank you.